Hi, this is Miss Litton, and this is my wonderful, excellent, super smart, bright, thoughtful, period 4 honors bio class. Say hi.
Hi.
All right, and we are going to talk about how we're going to analyze our roly-poly data today, and we're really sorry for those of you that are sick or ones who are gone today. We miss you already. All right, so for your roly-poly lab, you had your first choice chamber that you had was light versus dark, and so you let 10 minutes go by, and every minute you recorded how many were on one side and then assumed the rest were on the other side. Did anybody see any trend? Do you think they preferred light or dark? Just looking at your data that's in front of you, did you see any trend? What'd you get?
Well, a lot of our roly-polies eventually made their way to the dark.
How many? At minute 10, how many did you have on the dark side?
19.
19? How many roly-polies did you have?
20.
That's going to be statistically significant. I'm going to come back to that data. Good. Did anybody else get something different from that? Yes?
Most of our roly-polies actually have to go to the light side.
Go to the light side. Okay. So we see a difference there. So we'd really want to see how everybody did overall before we could probably come up with a trend line. Yes?
So at the start, ours went like more to the dark, and then some came back to the light, and then kind of went back.
Okay.
So it wasn't like right away.
How did you end up in 10 minutes?
After 10 minutes, we had 12 out of 18.
12 out. Okay. So you would have
Or 16.
expected, right? If it did.
Yeah, 16.
16. Okay. So if you didn't. Let's think this through just logically, not anything difficult. If you thought light and dark had nothing to do with roly-poly behavior, light and dark had nothing to do, and you had 16 roly-polies?
Yeah, 16. So it's
Okay, so how many would you expect on each side if light and dark didn't have anything to do with it?
8 and 8.
8 and 8. But instead you got
10 and
10 and 8. So 10, that's 18.
10 and 6.
10 and 6. So we're like, whoa, where did those roly-polies? They roly-poly babies. That does happen. All right. So you would expect 50% to be in the light and 50% to be in the dark, right? If light and dark didn't have anything to do with it. No connection between that behavior. And he got something different. He didn't get 8 and 8. He got 10 and 6. And we want to know, is that statistically significant that he got 10 and 6? That's what we're going to learn today, is how to judge whether or not is that something that we could say they preferred or not, okay? So your first was light and dark, and then your second one, I don't know what it was, Cheeto and no Cheeto. I don't know what you did on that one, but we'll analyze that data as well. And when we do the chi-square test, it's really simple. People think it's hard, it's not. Super simple. And this is a way for you to analyze your data to either accept or reject your hypothesis. Now, you learned about 2 words in your pre-lab, kinesis and taxis. You remember those? Which one is purposeful movement? Like, I would say that there was some purposeful movement if you had 18 roly-polies. 18 roly-polies? Yeah, which one is the purposeful movement? Which word? Kinesis or taxis? Taxis. And you know how I remember that? If I'm going to get in a taxi, I'm paying money. I don't want you to go randomly to different places. I want you to go to my spot. Kinesis is just random movement. So we want to know, did your roly-polies exhibit kinesis or taxis when they were given that choice chamber? And that's what we're trying to determine. So we want to know if our data can support our hypothesis, what your hypotheses were. When are the numbers significant? How do you know whether to accept or reject your hypothesis? And also you need to know what kind of hypotheses there are. So as a little review, I would like the oldest bio buddy to talk about this chart right here, and the youngest bio buddy to talk about how do you know when to reject. Go. I'm going to pause you. Okay. Why that's there. Okay, so we're back in. I think it's recording, yes. Okay. So on this one, we're kind of looking, the idea is that you have these hypotheses, you test them with an experiment. Some hypotheses you reject, some you will accept, and you'll move on. So how do you know when to start rejecting these hypotheses? Well, I need to review one other thing with you, and I'd like the youngest bio buddy. We're going to talk about two different types of hypotheses, but can you do a quick review of independent and dependent variables, please, youngest bio buddy? Go ahead. And specifically this model right here that you have.
Let's go again.
So, what was your independent variable in your experiments? Amount of light and whatever your other thing was. Yeah, your Cheetos, no Cheetos. Your dependent variable, your data, quantifiable data, numbers, right? Readings that you took. Not like, oh, the roly-polies seemed really happy. They were like skipping as they went to the other side. You had data. What was your data that you used?
The amount on each side.
Amount on each side, numbers, all right? Now, when you talk about the two different types of hypotheses, there's a research hypothesis and a null hypothesis. They are two sides of the same coin. Two sides of the same coin. Now, just for a minute, don't write, just listen. And then I'll give you time in practice, don't worry. A research hypothesis says there is a connection between your independent variable and your dependent variable. There's a connection there. If, then, because. If I give roly-polies a choice between light and dark, then roly-polies will choose dark because roly-polies live under rocks where it is normally dark. You see how I'm making a connection there? If, then, because. I'm saying I think there's some direct connection between that. That's a research hypothesis. That's identified as an H1. I could still do the exact same experiment, okay? But a null hypothesis, notice the zero, null, says there is no connection between roly-poly behavior and the choice of, going to light or dark. There's no connection with light and roly-polies. Their behavior will not change. Exact same experiment, right? All I'm saying is a research hypothesis is they prefer dark. The null hypothesis says doesn't matter how much light you have, it doesn't affect roly-poly behavior. Still the same experiment, right? If I do a research hypothesis, if I'm thinking along those lines, what kind of data would I be looking for to support that research hypothesis that I was going for? What would I be looking for? Yes? More roly-polies on the dark. If I was doing the null hypothesis, same experiment, I'm just thinking null hypothesis, I would be looking for what?
Equal or like
Yeah,
nothing.
same amount of roly-polies, whether it's light or dark, right? And in that case, what I'm assuming with the null hypothesis is what kind of behavior. If I have the same amount on the light and dark, what kind of behavior do they exhibit in relationship to the amount of light? What kind would that be? Kinesis. But on research hypothesis, I'm saying it's what? Taxis. Yeah, in that example, it would be taxis, right? So now, when you look at the data and you start looking at the numbers, take a look at this chart. Youngest, you went here, right? Oldest, you explain research and null hypothesis with the same chart. Look what I did up here. Go ahead. How is it modified? Go ahead. Okay, now come back to me. Let's say I have 20 roly-polies, okay? And I have one side that's in the light and one side that's in the dark. And if I thought light had nothing to do with it, how many would I have on each side? 10 and 10, okay? I can run this experiment, whether I'm doing a research hypothesis or a null hypothesis, I can run it the exact same way. And when I analyze my data, I can still analyze it 10 and 10. I expected 10 and 10. But with my research hypothesis, the way we wrote that particular research hypothesis, I would expect more to be on the dark side than the light. So I'd want there to be a big deviation. I'd want, instead of 10 and 10, I'd want maybe 18 and 2, right? If there's a big deviation like that, then that says, light has something to do with it, right? If it's a research hypothesis, I'm expecting there to be this big difference, right? If it's a null hypothesis, I'm expecting them to be, doesn't have any difference, I'm just expecting it to be what? 10 and 10. And I don't want a big change. It's still the same experiment. It's just where are you looking, what's your deviation? What's your deviation going to be? And is that deviation significant? Okay? Same experiment, just two different ways to look at it. So let's take a look why you might write something as a research and why you might write it as a null hypothesis. Somebody might propose that there is a connection between the amount of sleep you get and the grades you get in a class. So it says, is there a connection between the amount of sleep and the grades that you've earned? What would be a research hypothesis? What would be a null hypothesis for that question? Go ahead, discuss with your bio buddy. Okay. Now, research, I always remember this because see how the line, like H1, there's a connection between the independent variable and the dependent. It could be a positive connection, it could be negative connection, but there's some sort of connection. So in this case, I'm saying if students get at least 7 hours of sleep a night, then they will earn higher grades because they are more rested. Okay, I could put in a because there as well. Now I'm looking for data to support that. But are there other things that influence your grades, you think, besides whether or not you get 7 hours of sleep? What else? Raise your hand. Give me something that will influence your grades. Yes. Stress. Exactly. You'd be stressed out during a quiz or a test. Yes. Amount of effort that you put in. You know, are you studying? Are you reviewing? Yes.
If you ate breakfast.
If you ate breakfast, are you low blood sugar? Are you hypoglycemic? Were you see that? Yeah.
Knowledge of material.
Yeah, this is something you read about and study all the time. It doesn't really matter what the teacher says because you already know that, right? All of those things, you're right. Is there anything else you can think of that influence your grades in a class? Yes? Your teacher, sure. Maybe your teacher is very effective for you in the way you like to learn, or maybe that teacher is not effective for you in the way you like to learn. Maybe the teacher creates an environment where the teacher's saying, I love you. Do you know that I love you? Okay. Or maybe when your teacher, as soon as you're like, she hates us. I know she hates us. I know she hates me. Okay, then you're like, you're coming in and you're like, you're already dealing with those kind of emotions, right? All of those things. So when you say this is making the assumption, I get 7 hours of sleep, by golly, I'm getting an A in that class, right? Maybe no, okay? A null hypothesis would say there is no connection between sleep and grades. And that's probably not true, right? But do you see, by disproving the null, I am supporting the first hypothesis. I'm not saying it's the only thing, but I'm saying it is a what? Factor. You see that? I'm saying it is a factor, and that's more reasonable. Because it's not just getting 7 hours of sleep that's going to get you good grades. There are so many factors. But if I say there's no connection between sleep, and then I start collecting data. What's your grade? How many hours sleep? You have a Fitbit. I want to track it on your Fitbit, so I have quantifiable data. If I disprove the null, in turn, the one that says there's no connection, if I can disprove the no connection idea, I'm saying that there is some sort of what? Connection. It's almost like when you disprove it, it's kind of what you're going for, because you want to say, I think sleep does have some impact, right? So you will a lot of other things, but I think sleep at least has an impact on that. So we want to know how much of it is acceptable. When is it significant enough that we can say sleep does have an impact? Where do we draw the line? And that's when you're dealing with, is it just due to chance? Just chance that you got good grades, or is sleep one of those factors that gave you good grades? Is the amount of light, is it just chance that there are, let's say you had 9 roly-polies. Or, sorry, that's not enough to even be. Let's say you had 18 roly-polies. And you got 10 roly-polies on one side and 8 roly-polies on the other side. Do you think that's statistically significant? Okay, how about if you got 9 roly-polies and 9 roly-polies? No, that would be what you expected, right? What if you got 3 roly-polies and 16 roly-polies? Do you think that's significant? What did you get? 18 and 2, right?
19 and 1.
Oh, 19 and 1. Do you think that's statistically significant? I do too. Now, so when we want to do some sort of idea to how can we show this is significant enough that it makes a difference, or is it just due to chance? So let's do a little practice on how to go about doing that. If I were to deal out 20 cards, I have a deck of cards, and I were to deal out 20 of them, discuss with your bio buddy what would be a research hypothesis, what would be a null hypothesis for color of the cards, not suits, just color of the cards. What would be a research hypothesis, what would be a null? Still dealing 20 cards either way. But how would you approach it from a research hypothesis side? How about from a null? Go ahead.
If someone was to know 20 cards, the chance that being red or black is equal as there's the amount of cards we ever get. So the amount of red and black cards we get.
So let's do the research one together in an if-then because statement. If I deal out 20 cards, then what? How many would you expect to be red and black if I dealt out 20 cards? Then 10 would be red and 10 would be black because card decks come with half of them being red and half of them being black. Okay? That would be a good research hypothesis. And that may be on something like cards in that situation, you might be able to write one like that. Okay? A null hypothesis would be, if I deal out 20 cards, there will be a random number of reds and blacks. I can't, attribute it to one or the other. It could be, this many, right? Null hypothesis says color doesn't have any factor to it. There's no connection between having 20 cards and how many turn out red or black. So either way, do the same experiment. We deal out 20 cards. 8 were red and 12 were black. Is that significant? We deal out 20 cards. How many would you expect to be red? 10. And how many to be black? 10. But instead, I got 8 and 12. Is that significant? So there's a little bit of math that you do in order to analyze that. Okay? Watch me once. You're going to get practice on this. So I observed 8 red and 12 black. How many red did I expect? 10. And how many black did I expect? 10, right? All you have to do is take the difference. So I take observed minus expected. What is the difference here? How many was I off? -2. Now, if I wasn't red, I was black. So if I was down 2 over here, I must be what? Up 2 over here. Because I only had 2 choices, red or black. Okay? So then you just take how much were we off, and you square that. What is 2 squared?
4.
And because it's a negative times a negative, right? It's positive. Take the difference you got, square it, which is 4, and put it over what you expected, which is 10. Same thing over here. 2 times 2 is 4. Put it over what I expected, which was 10. What is 4 divided by 10? Use your calculator if you need to. What is 4 divided by 10? 0.4. Do you agree with that? And this one is also 0.4. Okay? Now, let's just think what we've done so far. We've taken how much we deviated from what we expected. We took both of those numbers, and what did we do to them? Squared it. Then we took that number and put it over what we expected. Okay? These are those 2 numbers. You add them up. What do they add up to be? What's 0.4 plus 0.4? 0.8. That is our chi-squared value. This is the number we use to look at a chart to see if our data is significant or not. So if you go here, okay, we took what I observed minus I expected squared over what I expected, same thing, observed minus expected squared over what I expected, and you write this this way. This is the chi-square value, chi-squared equals, this means the sum of the observed minus expected squared over what you expected. Oldest bio buddy, explain what this right here means, what I just explained. Go ahead, explain to them. Okay, now for us, what did we get our chi-squared value to be for that deck of cards where we expected 10 and 10 and we got 8 and 12? What did we get? 0.8. So now I just need to know, is that significant or not? Now, this says chi-squared equals 8. You do not square root it from there. Chi-squared is a value. It's a chi-squared test. So you don't do anything from it. That's it. That's all the math you do from there. So then this chi-squared number, chi-squared equals 0.8. So I need to look at a chart to see if this is significant or not. Now when I first open up this chart's going to look scary to you, but I promise it won't be. Just, oh, there's no chart there. Let me just tell you before we get to the chart, I want to know, I'm looking at this chart, like could it have been due to chance, this 8 and 12, or is it such a deviation, something else is at play? That's what I'm looking at. How much of this is due to chance? So I'm going to look at this chart, take a minute, just absorb it for a second. Look at how it's labeled. Okay, let's start with the degrees of freedom. Eyes are up here, not on your computer. Right here, degrees of freedom. What this means is this is what row you're going to pay attention. Your degrees of freedom is over how many options you have minus 1. Minus 1, and let me explain why. We had red and we had black. If it wasn't red, it was black. So our degree of freedom was 1. We only had one other option. If we were doing spades, clubs, hearts, diamonds, if we analyze that, how many choices did we have? 4. So we take 1 away from that. Our degrees of freedom really were 3. Okay. So our line that we're going to look at, because we just had red or black, is we're just going to look right here at degree of freedom 1. This is the row that's important to us right here. What was our number that we came up with when we did our math? 0.8. So I look over here, look, if my number was 0.004, our number was 0.8, that would have happened probably 95% of the time. And then we keep going. That would have happened 90% of the time, 80% of the time. So here's 0.15, 0.46, oh, 1.07. So our 0.8 falls somewhere in between those two. And that we would expect to have happened between 30 and 50% of the time. 30 and 50% of the time is okay. That's half the time. It could be almost half the time that it would turn out that way. Or 30% of the time it would turn out that way. Where we draw the line is right here. What percentage of the time would that be? 5%. Okay, if our deviation squared over what we expected added up together number was like really a big number because we had really big deviations, so when we squared the number it was really big, and when we divided in what we expected to that really big number that was that deviation squared, we would have this huge number. If we have a huge number, you know, if we had a number like 6, well 6 would happen between 1% and 5% of the time. That's not chance. Something's up, right? That deck of cards probably was not shuffled correctly or something along those lines. So if we have 1 degree of freedom, this is where we draw the line, right here. 3.84. At 3.84, we go, something was up with that deck of cards. Okay, let's try it again with a different experiment and see how you do, just to give you practice. If you want this, but I already explained that all to you, right? You okay with that? Okay. So now let's analyze something else. Right now, currently, if you look, and this is of data of 2016, if people checked what their job was, checking the box, I'm a chemist as my line of work, 35.2% of chemists are women. So is that statistically significant? Because if we said gender doesn't have any impact on what job we would do, we would expect how many of the chemists to be women? 50%, and we would expect what? 50% to be men. So if somebody said, oh, there's not a problem in our education, there's not a problem with how we raise our children, that's okay. 35.2% is acceptable. That's not outside the range of possibility. So is that chance that 35%, or is that a statistically significant number? Well, what can we do? We'll apply the chi-square test to it. So how would you start? How would you start with the math? What would you say? Do you know what's observed? Do you know what's expected? Talk it over right now with your bio buddy. How would you set it up and start to set it up on your paper right now? Your practice paper. And if you need a little help, here's this. You need a little help, and I'm going to pause you for a minute. Okay, let's see where you're at and see what I can do to help. Okay, take a look up here. So I observed, right? 35.2. That was the only number I gave you. But if you're assuming 100% are people, and if you could only be identified as male or female, if 35.2% were female, then that would mean what? 64.8% had to be male. And I'm writing it as a null hypothesis. I'm saying I expect 50 and 50, and hey, it's no problem. 35, no problem. So I'm putting 50 and 50 right here. So I take the difference. What's the difference right here? 35 observed minus expected equals what?
Negative 14.8.
Negative 14.8. And then this would be what?
14.8.
Yeah, because we didn't have any other option. So when you square 14.8, what is it? What do you get out to be?
219.04.
219 point what? 04. So we'll just say 0, right? And this would have to be 219 as well, right? Then you take 219 and divide it by, what did we expect?
50.
50, and over here, what? 50, and what does that number come out to be?
4.38.
4.38, so what do we say that is? 4.4, and this one is 4.4. And then remember, we do the sum of those. So 4.4 plus 4.4 equals?
8.8.
8.8. Does that sound like it's significant? It might be. So now we just need to go over here. This is what we did, right? Okay, and we got 8.8. I said degrees of freedom 1. If you weren't male or female, then you were the other one, right? So I only have 1 degree of freedom. So now here's just another chart. Okay, and I go to 1 degree of freedom. I'm looking for 8.8. I'm looking for 8.8. I am looking, and no. That means the deviation squared over what I expected and added together is so great, it would happen less than what? 1% of the time. Less than 1% of the time would that happen. So I expected 50-50. I got 35 and 64. That deviation squared and added up together is so huge that that's not due to chance. My chance line was at 3.84, right? Or somewhere in there. This is stepping into, this is statistically significant. So there must have something to do. There is therefore a connection between gender and job choice. Gender has an impact. It's not the only impact, but it does have an impact. Yes?
So does that mean like that if it was purely up to chance, it would happen less than 1% of the time?
If it was purely up to chance, I would expect a very small deviation. Like if, let's say we got, instead of 50-50, let's say we got 47 and 53. I bet that is statistically insignificant. I bet that's a smaller number. You could figure it out, right? It would be easy for you to figure out. But I bet 47 and 53 is not statistically significant. All right, so now let's try it another time here. Let's deal with a deck of cards. And this time I want you to take into consideration the suit as well. Okay? So figure out how you would set this up. How would you set up your little charts? What would be the math that you would do? You don't have to do it in a chart form. I was just doing that to keep it straight. How would you analyze this? Is there a problem with my random card generator? Or is this okay for clubs, diamonds, hearts, and spades? Go ahead and work that out.
So it's not good.
All right, let me help you out in case you're struggling just a little bit. How many would I expect of each of these? 5. I agree. how many did I observe of clubs?
6.
So it'd be 6 minus 5, what? Squared. And how many here? 3 minus 5 squared. And here, 3 minus 5 squared. And how many is it? 6? 8. Oh, 8, I'm the one who did it, squared. And you would take each of those numbers that you got and divide it by what you expected. Is that accurate? And then you would add those up together. Tell your bio buddy, did you do that much? You may have set it up like this, right? That would be one way to keep it straight, but you can do that just by a series of equations. So you probably got something like this. You agree with that? Okay. And so I just sum them up. I don't square root it. I just say my chi-squared value is 3.6. Raise your hand if you got 3.6. Good job. So then I said degrees of freedom were 3. Oldest bio buddy, justify why I'd say degrees of freedom were 3. All right. So now I'm looking at the chart. Degrees of freedom is 3, so I go down to 3. I'm coming across, what number am I looking for? 3.6. I'm looking for 3.6 somewhere here. Between what percentage of the time? 50 and 20%. Can I accept that? Yeah, chance could have made that happen. I'm not thinking we're over here in this poor fit range. Chance could have made that happen. All right, so now let's apply this. Let's apply this idea to our roly-polies. Now remember those two words. Was it just kinesis, random movements that put 10 roly-polies on this side and 8 roly-polies on that side instead of 9 and 9? Or was there taxis? Was there purposeful movement? Same experiment. Always, the way you are going to want to do it is you can't say, oh, I think it's going to show taxis if I have, let's say you had 14 roly-polies, 10 and 4. It has to be 10 and 4. No, you don't have to say that. You can just say, you can still say, I think there's 7 and 7. You just say, is that number off so much that there was a reason? I think there was some other reason why they went to one side or the other. So you want to do this for at the 10-minute mark, whatever your roly-polies were at 10 minutes, we'll assume that was enough time for them to decide where they wanted to go, if there was a decision making, and then analyze it from there. So for that, let's take let's take your example. I'm going to get rid of these numbers here. Let me get rid of these numbers that are already here. All right. So now, how many roly-polies total did you have? You had 20. So if you had 20 roly-polies, how many would you expect in the dark? How many would you expect in the light if it was pure kinesis, random movements? 10. We would expect 10 and 10. Are we all right so far? Okay, and we could do this as practice on here because this is what you would be doing. You would do this for each of your two sets. You know, you have your light and dark and then your Cheeto, no Cheeto, whatever that is. Okay, and how many did you observe in the dark? 19 and 1. So 19 minus 10 is what? 9. And 1 minus 10 is negative 9. So let's do it then. 9 times 9 is what? 81. Because I squared it. Over what I expected was 10. So what is 81 divided by 10? 8.1. And the same thing here. 81 divided by 10 is 8.1. I sum it together. What's that going to be? 16.2. How many degrees of freedom did we have? 1. Okay. Okay. That would have happened less than 1% of the time if they were doing kinesis. So there must have been. That gives us evidence that for their experiment, the way they set it up, there was taxis. Now, could their experiment be perfect? No. Could there have been somebody from period 2 who had sugar water And so they put their sugar water, there was still residual sugar on the dark side, so it wasn't really dark, it was because there was sugar water, right? That's why we do the experiment again and again. That's why we look at more than one set of data to see, was that a fluke? Could there have been some other variable? Because that data right there clearly shows that they prefer dark over light. But is that the trend we see in the rest of the class? Or does it look like it's more like kinesis? So we would maybe need to repeat that experiment or kind of put all of our data together. So this is what you're going to want to do at the 10-minute mark. Now take a look at your rubric. Take a look at your rubric. Because there would be a sense of confusion because I think I put it in the lab map a little bit different than the rubric. Okay, but let's go through how I'd like it to be. If you did it the other way already, it's okay. But you have your background, your hypothesis, your flow chart, your data table. What comes after your data table? Graph. So let's talk about your graph. Your graph, I would like you to graph dark and whatever your other thing was, Cheetos. I don't know what it was. You only need one line, and I believe I said this in the lab map. You only need one line because if you were going to graph dark and light, it would just be the opposite. It would just be this cute, neat art thing that you made because it would be the right. If one is 7, the other one's 3, and if this goes up, then that one's 3, right? So we don't need to do that. We just need one line, just graph dark and Cheeto, whatever your breadcrumbs, whatever it is. Okay, dark and Cheeto. Now, when you make your graph, don't go, you'll have 0 there because you could have 0 roly-polies on one side, right? But you're not going to start your line at 0. You would start your line at 5. They all started at, or however many, you know, half of your roly-polies are. That would be what it was at time 0, right? Time 0 is whatever half your roly-polies are. If you had 14, it would start at 7, right? And then you would go from there. Okay, that is your graph. Make sure you're, yes?
Can you explain how we would do the lines one more time, like the Cheetos and the dark on the same?
Oh, yeah, sure. You would just do, let's make a new page. So I don't know how many roly-polies you have, but using the example that we had, remember you do your independent variable and then your dependent variable is your data. So you could have 2 lines, right? You could just have number of roly-polies, right? Because that's what we're measuring versus time. So you would have time 0, 1, 2, 3, right? 4, 5, 6, 7, 8, 9, 10, right? And then you would have number of roly-polies. If you had 20 roly-polies, that would be here, 10 roly-polies, it would be here, 5 roly-polies, and 15, right? So if I was doing the light and dark, at time 0, you had 10 roly-polies, right? Time 0 is 10 roly-polies. What did you have at 1 minute?
Wait, are you talking about?
Yes.
Oh, sorry.
I've used your data all the time, so.
Sorry,
5. Okay, so, and this is for dark, right?
Yes.
Okay, and then what did you have at 2 minutes?
5 for light, I did the light.
15.
So 15.
15, right. Okay, and at 2 minutes?
15.
Also 15.
Okay, and at 3 minutes?
15.
And at 4?
16.
And at 5?
16.
I remember this is an estimation.
15.
Back to 15. And at 7, you see my point here. And then you would draw your line showing me what happened. And you would label that as dark, right? Then you add, what was your other variable?
Baking soda.
Baking soda, okay? So at baking soda, you started at 0, yes?
Yeah.
Okay, what was your next one?
14.
14 at 1 minute.
And then.
And I would probably do this line differently and like,
Different color.
yeah, different color or dashes, right? And then you would label that. Yeah. Okay, so that goes your graph. I would have room for a title, right? Yes.
When you're labeling them, should you just like make a key and do it?
Yes, make a key.
And do a color. Okay.
Yeah. Okay, then after your data table okay, we have graph, and then what comes after the graph? Calculations. 2 chi-square equations written out, final answers box, includes all the units. Right? So show me your math, make it neat, make sure I know this is the one for light and dark, this is the one with, what was your second one? I already forgot it.
Baking soda.
Baking soda. No baking soda. right? Yes.
So do we have a chart that says if it's significant or insignificant?
You will tell me significant or not significant. And I gave you a chart in Google Classroom, but you could Google, you know, a chi-square data chart too, but I gave you one in Google Classroom. Okay, and then when you do your claim evidence reason, don't do claim evidence reason because you can just do your claim together. Like, I don't know, how did your roly-polies turn out with baking soda?
They stayed about around 10 minutes.
All right, so you could say, based on your experiment, I could say roly-polies preferred the dark. They did not mind baking soda. That would be my claim. My evidence, then I would give my evidence from the chi-square test that it was statistically significant or not significant on what they chose. And then I would give my reason, you know, and I would say, you know, I think they did taxis, right? You know, or you could use even kinesis and taxis in your claim. That would be even better. They exhibited taxis concerning light, but they exhibited kinesis to baking soda. And then you give your reason why you think that is. I think they prefer the dark because that's where I find roly-polies. Baking soda, the pH must not affect their body. It doesn't, you know, something along those lines. And then error. Why you think what error? That's not due to your fault. Okay? And so you can do the claim together, then you provide evidence, then your reasoning, you could just talk about roly-poly behavior, and then your error. And then you finish up with your conclusion. Our data did support our preference for, you know, no light. It did not support baking soda. Because you probably thought it would go away from the baking soda. That's what I would have guessed. Yeah. So, and then that's the end, right? Yes.
I don't know if this matters.
Whose did I take? Okay.
I don't know if this matters, but on the roadmap.
Yes, I know that, and that's the part I wanted to address is the confusion, because I put the when you have calculations that you have from your data table, you usually do it right underneath your data table, but I wanted you to have it under your graph. If you already did it, don't worry about it, but follow the rubric if you can. If you haven't already done it, follow the rubric. If you didn't, it's okay.
I have a question also, and roly-poly is spelled with one L instead of two on the.
Okay, I know it's not statistically significant here, but yeah.
That matters.
No. Okay, any other questions about that? Okay, you're awesome. Work with your team. I'm going to pause this. I hope you're having a great day, and see ya. Have some toast.